Hey guys, welcome back. In this video, we're going to talk about factors affecting equilibrium and how they change. All right, so the question that we're going to pose is what happens when reactants are added or removed when products are added or removed the pressure changes or the temperature changes. All right. These are our macro conditions, P, V, T, right? What happens? That's a good question, right? So, for example, some of you, right, because we live really close to a marine base, so some people might know people who've gone to the mountains. And if you go to the mountains, whether you're a hiker or whether you're in the military or whatnot, there's an adjustment because the amount of oxygen in the atmosphere is different at higher elevations. And so it's harder to breathe, and your body adjusts. And your body adjusts by adding more hemoglobin, right? So if we oversimplify that reaction, Hb hemoglobin plus O2 going to oxyhemoglobin, right? If one of those concentrations is off, right, what does your body do? Right? The system will try to restore equilibrium. Right? We try to restore equilibrium. So just even an exercise with breathing, right? We breathe more to get more oxygen in because our oxygen levels in our body are not where it needs to be because we're using it more, all right? And so we need to know how this reaction is going to restore equilibrium. So there's something called the reaction quotient Q, all right? And so if we look at the reaction quotient Q, and it's the same thing as products over reactants. You may think, hey, that's the same as our equilibrium constant K. And you'd be right. What's the difference? It's not necessarily at equilibrium. Right? So this tells us where we are, okay, in our situation, in our reaction. And what this does, it predicts how a reaction will change or shift. Right? How it's going to move. All right? So you can think of this, right, as big, long. Oh, that's not what I wanted at all. Perfect. Big, long teeter-totter. And in the teeter-totter, I don't know if you guys ever had one of these before. Got to play with one. Of course I did. And it wasn't always as fun as I wanted. So we have reactants and they have some amount to them, right? There's some mass there on the teeter-totter, and we have products. They have some mass there, right? So think of it like this way. And if we added more reactants, the teeter-totter then would start to look like this, right? And so some of these would have to come back over here, right? Some of the reactants, so if I had that many, it was too much. Some of them would have to come to the product side, and the reaction would shift. Weight would shift to products, okay? Now, for humans, it would be like me, my sister, right? And then my sister jumping off and running to tell Dad that I did something mean to her, which I probably did when I was that age, and so that's why I don't do teeter-totters, right? But for chemicals, we have a ratio of products to reactants, and so if this ratio is off, they can go back and forth to make the ratio correct, right? And so there's three options here with Q, all right? So Q has three options compared to K. Obviously, if Q equals K, we're at equilibrium. So if we're at equilibrium, there's no changing going on or whatnot. Now, if Q is smaller than K, so let's say Q is smaller than K, what that means is what? The products are too small, right? Not enough product. Or too many reactants, right? Okay, the denominator is bigger than the numerator, or what it should be, right? So this means we will shift, the reaction will shift right to products. We want to make more. Right? And so in this situation, some of these reactants would come over to make products. And so the products would actually be smaller now, or sorry, the reactants would be smaller and the products would be bigger. And that's how to restore equilibrium, to make sure we're balanced. Okay? And then conversely, if Q is bigger than K, right, that means the numerator is too big, right? Too many products or not enough reactants. The reaction shifts left to reactants. All right, think of it as just a restoring equilibrium. It's making the teeter-totter level, whatever it is. Now, these numbers, it doesn't matter what the numbers are. This number can be 10. Oh, I don't want to use a real pen. I want to use this could be 10, and this could be 10,000, right? But if this goes to 100, now our ratio is off. So some of those 100 have to go over to products, if that makes sense. That's right. So it doesn't matter what the numbers are. We're just restoring equilibrium. So that is the reaction quotient. It tells us where we can calculate where we are. Like, oh, that's not equilibrium at this temperature. It's going to shift. Or that is equilibrium. It's good to go. All right. Which leads us to the generality, speaking of this, which Le Chatelier his principle. Chatelier's principle. I think there's a little I don't know what it's called over the A. So now, his principle says when a stress is applied to a system, at equilibrium, the system will respond by shifting in a direction that minimizes the effect of the stress. Right? The goal is to restore equilibrium. So this is very similar to Q, but we're just looking at the disturbances in general. We're not going to calculate it. Q you calculate. This is more of a predictor. All right? And so the disturbances. Well, obvious one is concentration. So there's a couple things. You can add reactants. And that means we will shift to products. All right. If you add products, we would shift to reactants. So products would be to the right. Reactants would be to the left. So when you say, oh, it shifts right, well, it's to products. Oh, it shifts left to reactants. Now you could remove reactants. And in that case, we would shift to the reactants. Shift left, right? Because if you look at the teeter-totter again up here, right? If we just remove, right? If we remove this, you guys know the teeter-totter will start to go down, and so the teeter-totter will look like this. Well, let's try it more like this. We don't want the teeter-totter to look like that. And so you have to take some of the mass that's over here and move it this way. All right? So I like the teeter-totter analogy for that. But it's actually reactants going to products or products going to reactants. And then finally, if we remove products, we're going to shift to products. All right, so those are our concentration. All right, that's what we get with concentration as a disturbance. The next one is temperature. And so, if something is exothermic, so for exothermic, heat is a product. So we're just going to treat heat as a product. So if it's exothermic and we add temperature, we add heat to the system, it means we're adding a product and the reaction will shift away from the products. If we remove heat, it will shift towards the product. Now, if we are endothermic, right? Heat is a reactant. Okay, and so if heat's a reactant, if we add heat as a reactant, the reaction shifts right to products. If we remove heat and it's endothermic, the reaction will shift left back to reactants. All right. And then finally, pressure and or volume. Okay. So if we lower the pressure, lower the volume or increase pressure. So whether we, like, a lot of times they're related. So if I have a container and I reduce the size of the container, the pressure is going up in the container, right? It's like if you squeeze a balloon. So if we lower the volume, we increase the pressure. That means, all right, the reaction moves to fewer particles. All right, so if you go back to the ideal gas law, all, gases are virtually points and they take up very little space. Right? And they have elastic collisions and no attractions and whatsoever. But if we actually do lower the volume, make them closer and closer, right? If I have 5 moles of reactant gas and 3 moles of product gas, right? Well, 3 moles of gas takes up less volume than 5 moles of gas. And so if we shrink the volume, it'll go to wherever side, in my little verbal analogy here, the product side, with 3 moles of gas versus the 5 moles of gas, right? So where it goes to wherever it takes up less space. And the opposite is true. If we increase volume or lower the pressure, right, the reaction moves to more particles. All right, and so wherever side takes up more space, it'll go to that side because there's more space now. All right, so that is factors affecting the equilibrium. Don't hesitate to reach out, and we'll see you next time, guys. Goodbye.